So yesterday we kind of went over that stuff on a page 371, 372 assignment from Monday. Today we want to wrap up the unit and get you guys ready for your unit test tomorrow. So we talked about this a little bit before, called phase shift. The phase shift is a number that goes inside. If we have y equals sine of x plus 90 degrees. Of course, the equivalent of this would be y equals sine of x plus, what's the radian equivalent of 90 degrees? Pi over 2, exactly. So those are both the same. If we label our graph here, (180 degrees, 360 degrees), this would be pi, this would be 2 pi if we're labeling it in radians. What does the 90 tell us? The plus 90. Well, it tells us that the 0 is acting like it's 90 degrees. So if we were, remember we said our starting point, our origin is if we set this equal to 0, x plus 90 equals 0. If we solve that for x, what do we get? We subtract 90, we get x equals negative 90. That is where this curve starts, is at negative 90. Or a negative pi over 2, if you would like. It's a sine wave, so that is at equilibrium at 0. What is our wavelength or period here? I guess I should call it a period because it's been using. How many degrees? Well, remember, we just take this value here, x equals, set it equal to 360. Or if we're using this one, it'd be x equals 2 pi, either way. So from 90 degrees, if I add 360, where do I end up? Negative 90 plus 360 is 270. Or 3 pi over 2 if we're going in radians. So that is the end of the wave. Now there's an equilibrium point in between the beginning and the end, and it would be right in the middle. Where would that be for this wave? I could find it if I can't just find it by looking at the graph. This thing's being a pain today. It's just something screwed up in Word. I don't know what it is. Anyway, we've got negative 90 degrees is one end, 270 is the other end. We can add them together and divide by 2. Make sure if you do this, you add them and you hit equals first, and then you divide by 2. Negative 90 plus 270 is 180. Divided by 2 is 90. So 90 degrees is the center point between those. There's equilibrium there. Now this is an amplitude of just 1. So go up to positive 1 down to negative 1. Here's our wave. Like that. Now again, note that this part over here probably wouldn't be included because it's before our beginning of our graph. But we can put it in there to help us sketch it. Which means we should probably continue here to at least that point. We can keep going if we wanted to, but we should at least complete one full cycle within the graph. Can you think of another equation other than y equals sine of x plus 90? Another equation that would give us that same graph? Come on. Yeah. Y equals cosine of x would be that exact same graph. Remember, y equals cosine of x is equivalent to sine of x plus 90 degrees, or sine of x plus pi over 2. Sure, now it clears up. Okay, so why is this true? Let's talk about that. Unit circle time, right? First of all, let's say I've got cosine of 20. That should be equivalent to the sine of what? Remember, cosine means the sine of the complement, right? What's the complement of 20? You got it, 70 degrees, 90 minus 20. Complement means they add up to a right angle, or 90 degrees. So sine of 20, or cosine of 20 equals the sine of 70. But let's look at that sine of 70 degrees here. This is the sine of 70 right here, right? There's another spot that has that same sign over here. That's going to have a reference angle of 70. It's the supplement of 70, right? What is 180 minus 70? Yeah, 180 minus 70 is 110 degrees. What is the difference between 20 degrees and 110 degrees? 90 degrees. Let's try that for a different value. Maybe that's just a quirk for 20 degrees. Somebody give me a value between 0 and 90. Not everybody at once. 64, very good. So the cosine of 64 is going to be equivalent to the sine of what is the complement of 64? 26, okay. Well, the sine of 26 is equivalent to the sine of, what's the supplement of 26? 154. Does that differ by 90 degrees? Say yes. 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 It always will. So the cosine of an angle is always going to be equivalent not to just the complement of that angle, but also the sine of the complement of that angle, but also the sine of that angle plus 90 degrees. So that's why the graphs are offset by that 90 degrees. So I'm going to have you guys try one. Y equals cosine. I'm going to use theta instead of x because that's what the book uses. And I'm going to use pi. I'm going to use radians instead of angles. Now, when I see something written like that as minus pi radians, what does pi radians stand for in degrees? Yeah, put 2 pi over 180, or not 180, 360. Cancel out the pi's. 360 divided by 2 is 180 degrees. So this is equivalent to y equals the cosine of theta minus 180. So in your notes, graph that for me. Okay, so let's deal with the phase shift here. We'll go out this way. We're going to start at 180 degrees. Actually, not 180, but what? Actually, it is 180 degrees, right? This is the starting point, positive 180. Because if we solve this, x minus 180 equals 0, or theta minus 180 equals 0, theta equals 180 is at 0 point. So that's the starting point. What's our period here? 360. So 180 plus 360 is 540. So 540 is the end of that cycle. Now 180 is, since it's a cosine, it would be at what value? At 1, positive 1. So right there. Where would our first equilibrium be? 270 right there. Our trough? 360. Next equilibrium? 450. And then up to our peak again right there. Now we've got to work our way back here. According to this pattern, what would be happening right here at 0 degrees? Another trough. Very good. That's 180 degrees away. 180 degrees that way is right there. So it's a trough. This is going to be an equilibrium. It's just a matter of tracing that wave backwards to 0, and there it is. How many of you had that? Josh? You had that grin like the cat that just ate the mouse. So then, it's a little funny. Try that one. Okay, so here's our graph. I'm going to label this out for us here quick. So let's find our starting point. Tell me how to find my initial point. Three x plus 180 equals 0. So we solve that for x. We get that x equals negative 60. So that means we've got to work backwards here. Find negative 60. That's negative 90. Negative 60 will be right there. There's my starting point. What is my period? For the period, remember, I take the part here without the phase shifts. 3x equals 360. I said equals 360 instead of 0. I solve that for x. What do I get for x? X is 120. So negative 60 plus 120 would be negative 60 plus 120 is positive 60. So positive 60 here is the other end of that cycle. Now we bring in the amplitude. It's a negative 2, which means you go up to positive 2 and down to negative 2. But what else does it mean? We're flipped over, right? This is sine, so we start out at equilibrium. There's equilibrium at the end. There's an equilibrium where in the middle? 0, right in the middle. This would normally be a peak here, but since it's a negative 2, it's a trough down here. This would normally be a trough, but the negative 2 means it's the peak. Now I should go one more half cycle at least, so I get a full cycle after 0. So again, this part normally wouldn't be displayed on the graph, but that's what it would look like. Because of the phase shift, it looks like it's just equivalent to y equals 2 times the sine of 3 theta. Does that make sense? Okay. So we can have phase shift in our AC waves. So we might have our voltage is equal to our peak voltage times the sine of 2 pi ft plus pi over 4. If I ask you find the voltage at 3 milliseconds if the peak voltage is 170. So what goes in for VP? 170 times sine of, what goes in for F? Standard AC frequency is 60, right? So 2 pi F is 2 times pi times 60. I'm going to write that in as 120 pi. What goes in for T? 0.003 for 3 milliseconds plus pi over 4. So I'm just going to punch that in the calculator. 170 times sine. This is 120 times pi times 0.003 plus pi divided by 4. 5.68 volts. So we're really close to an equilibrium there. If we started out at 170 volts, at that point we're at 5.68. Any questions? A little bit of review. First, RMS. What's the magic number for RMS? Square root of 2. So if I told you my peak voltage is 170, how do I find my RMS voltage? Got 170 divided by square root of 2. 120.21. If I tell you that my RMS voltage is 60 volts, how do I find my peak? Yeah, 60 times the square root of 2. Giving us 84.85 volts. Easy enough? What if? Can we go back up? You got it all? There. Is that better? You ready? Okay, let's say I give you this wave here. If I ask you for the period of that wave, period goes from here to here. 12 milliseconds minus negative 2 milliseconds, which gives us 14 milliseconds, the period. If I ask you for the frequency of that wave, how do I find it? 1 over 0.014. So 1 divided by 0.014, otherwise known as 71.428571426. 71.43 we'll call it. That is hertz or per second, however you want to list it. Now, assume it's an EM wave. What's EM stand for? Electromagnetic, yes. The velocity of an electromagnetic wave is 300,000 kilometers per second. Velocity, though, we said earlier, is equal to wavelength times frequency, or frequency times wavelength, right? So if I wanted to know the wavelength of this wave, that's the lambda, right? That wavelength is going to be equal to the velocity divided by the frequency. We know the velocity, 300,000 kilometers per second, divided by 71.43 per second. The per seconds are going to cancel out. We're going to be left with kilometers. So 300,000. I said 300,000 or 300 million. Should be 300,000. Why did that wrong? Should be 300,000 kilometers. It'll be 300 million meters per second. But we can leave it as kilometers. So 300,000, I should say. Sorry about that. I was saying 300,000, but writing down the wrong thing. Divided by that wavelength of 71.42. There's something very fun. Let me try that again. We have 4,200 kilometers is our wavelength. What if I ask you for angular velocity? What's the symbol for angular velocity again? Omega. Very good. Omega is 2 times pi times f. So it's 2 times pi times 71.43. 448.8. That's going to be in radians per second. Does that all look familiar? A little bit. Now here's the part we haven't discussed. Find the phase angle. Let's go back up here. The phase angle is really not that hard to find. The period of this thing is 14 milliseconds, right? How far is it between the start of the wave and 0? 2 milliseconds. A full wave is how many degrees? 360 degrees. So how many degrees is our phase, or this piece? We just cross multiply and divide. It is a simple proportion. 2 times 360 divided by 14 is 51.43 degrees. Is that a plus or a minus? Well, if we're not sure, let's set x equal to negative 51.43, but we want that to be solved so it's equal to 0, right? We would have to add 51.43. x plus 51.43 equals 0. So it would be a positive 51.43 degrees. It is a positive phase shift. When the wave starts on the negative side, it starts before 0, that is a positive phase shift. If the wave started after 0, that would be a negative phase shift. So if we wanted to write the equation for this, we could. The equation would be y equals, now I didn't ask for the amplitude here, but what is the amplitude? 7. So the amplitude would be 7 times the sine of, our period was 14 milliseconds. Our frequency was 71.43, so 2 times pi times 71.43 times t plus that phase shift of, how do we write that in though? Well, we've got to do was that negative 51, was it 0.43? And then we've got to, shoot. We start out with that phase shift like that. Now we've got to work our way backwards. So we've got to multiply by all of this, right? So it's negative 51 times 2 pi 71.43. So it ends up being, holy crap. Oh, shoot. That's in degrees, isn't it? So it doesn't work. What do I have to convert it to? Radians. So we've got to convert that to radians first. Sorry. So let's clear this out. We have to do the negative 51.43 times 2 pi divided by 360 to make it into radians. So it's a negative 0.897 radians. Then we can multiply by 2 by pi and by 71.43. That's our phase shift, 402. So this is actually going to be 402.86. So it goes in there. Now for the test tomorrow, I won't ask you to write an equation like this off of a wave like that, because that phase shift used to be really weird because of this angular velocity here. The ones that I'll ask you to work with will have nice even numbers there for that period, to determine the period, so that it won't be such an ugly phase shift. I probably should have not done that last part there, just so I didn't confuse you. I worked backwards. Technically, it's negative 0.8976 because I converted the negative 51.43 to radians. But then I needed to get it into this form here. So I had to multiply by the 2 pi 71. So this is now 2 pi 71.43 t equals a negative 402.86. And then I had to get it equal to 0, so I added the 402.86 to each side. 2 pi 71.43 t plus 402.86 equals 0. So that gives me what has to go in those parentheses. It's kind of an ugly calculation. Yes, sir. The whole thing? Okay. Should I do the same problem or different numbers? Sure. Sure. A little bit. Okay. In your packet, page 374 through 375.